Hello everyone. Let's get started with section 5.5. This is going to be our um, mean and standard deviation of a discrete random variable. And so um, before you were taking population means, and we had finite populations, meaning that we could count them, and so that's why we were able to use the formula you see below to do a population mean. Now we can kind of extend the same concept to a population distribution or a discrete random variable. So notice we're going to use the same formula, but instead of calling it just mu like we have done in this particular case, instead of the letter mu here, notice we call it mu sub x. Um, Mu sub x, and so that just lets you know that it's a discrete random variable rather than a regular population mean. Okay, so for example, here we have some populations, and so let's go ahead and find our population mean, which would have been 19 plus 20 plus 20 plus 19 plus 21 plus 27 plus 20 plus 21 all over 8. All over 8. So at this point, you know that you could very easily punch this out in your calculator, but I want you to look at how we could use probability distribution to help find this mean. Because watch what happens here. Notice I've got two 19s in here. So 19 times 2. Notice I've got 3 sets of 20s in here. Notice I have 2 sets of 21s. And 127. Now I can divide that out even further, and I can say that this is 19 times 2 eighths plus 20 times 3 eighths plus 21 times 2 eighths plus 27 times 1 eighth. Now if you notice, that's the population distribution there. Okay, so what I'm actually saying here is this. I'm actually telling you this is 19 times the probability of x equaling 19. So this is the population distribution. So plus 20 times the probability of x equaling 20. Plus 21 times the probability of x equaling 21. Plus 27 times the probability of x equaling 27. Because the probability of x equaling 27 is 1 over 8. The probability of x equaling 19 is 2 over 8, and so on. So what we can essentially say is this, is that the population mean is the same thing as the sum of x times the probability distribution. So this is the formula that we will be using to find the population mean of a probability distribution or a discrete random variable. Okay. Now sometimes we call this, as I said, that we denote this with an x here, so we know it's a so that we know that it is a discrete random variable, and sometimes we call that population mean expected value or expectation in place of the word mean. So don't let that be a burden if you see that. All right, so at this point, let's look at this is the formula. So we just proved the formula. So let's look at the next example. Well, there's the formula. Now, Prescott National Bank has 6 tellers available to serve customers. The number of tellers busy with customers at, say, 1 p.m. varies from day to day and depends on chance. Hence, it is a random variable. Past records indicate the probability distribution is shown below. Find the mean of the random variable x. So remember, mean of the random variable x. First of all, notice they gave you the population distribution right here. These first 2 columns would be your probability distribution. That's your probability distribution. Now this last column here, this is your population mean. This is the formula that we just talked about just a moment ago. Now notice what this is. They took 0 times the probability that x equals 0. They took 1 times the probability that x equals 1. They took 2 times the probability that x equals 2, and so on. And that's how they got this right here. They just multiplied the first 2 columns together, essentially, is what they did. Now, that's to find x times the probability of x equaling x. This column here. Just multiplying the first 2 together. Now, notice this right here. Sum. So to find the mean, we have to add all these together, which is what they did down here. So this mean is 4.118. 4.118. Okay? So they multiplied the first 2 together to get the third one. Took the sum of it. That was our mean of our discrete random variable. So the law of large numbers says that if in a large number of observations of a random variable, the average of those observations is approximately equal to the mean. Okay, so the larger the number of observations you have, the closer you tend to be to the population mean. That's basically what it's saying there. Okay, so just have an idea behind that. The more observations you have, the closer you actually get to the mean on average. Now, similar reasoning lets us also apply this same mode of thought to standard deviation. So here's our computing formula for standard deviation. This is the one I'm going to use when I do my calculations. I would recommend that you use the same one. Okay, so that is, the other one is our defining formula. It's a little bit more complicated to try to solve for. But notice the shade of difference here. It's the sum of x squared times the probability. Okay? The sum of x squared times the probability. So, that being said, let's look at one of these. Alright, so here's our problem from before. So, we have this. And they're asking for this time we want to find the standard deviation. We're not, ignore that right here. Let's find the standard deviation. Okay, well, remember what the standard deviation formula says. It's the sum of x squared times the probability distribution minus the population mean squared. Minus the population mean squared. Okay, so here's what we have. We have x. We already know that over there in that right hand side. 2, 3, 4, 5, and 6. We have the probability distribution of x, and that's 0.029. That is 0.049. That is 0.078. That is 0.155. 0.2. 0.212, 0.262, and 0.215. Now, x times the probability distribution. Now, why do we use this? We need this to find the mean. Okay, we need this to find the mean. And so remember how we find this. Now, I know it's already given over here for us, but remember how we find this. 0 times 0.029 gives us 0. 1 times 0.049 is 0.049. 2 times 0.078 is 0.156. 3 times 0.155 is 0.465. 4 times 0.212 is 0.848. 5 times that is going to be 1.310. And 6 times 0.215 is 1.290. So when you take this sum, that gives you the 4.118. Now, in the large scheme of things, when you're trying to find your standard deviation, that is our mu here. That is what we're looking for right here. Okay? So that's the second half of the problem right there. Now, we have to just add a little bit. That's how to get the population mean. Now, the other part that we need to get the standard deviation is the x squared times the probability distribution. So first of all, make yourself an x squared column. And so 0 squared is 0, 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, and 6 squared. So there's our x squared. Now, we also need an x squared times the probability distribution column. Okay? So, that's going to be the x squared column times this column here. Okay, we already have the probability distribution. Now we have the x squared, so we just need to multiply them together. So 0 times 0.029, still 0. 1 times 0.049 is still 0.049. 4 times 0.078 is 0.312. 9 times 0.155 is 1.395. And then you've got 16 times 0.212 is 3.392. 12 25 times 0.262 is 6.55. And 36 times 0.215 is 7.74. So that's going to give us a 19.438 when you add that. Because notice, we have to take the sum of it. So that's why we added it up. So that's going to be 19.438. Okay? So do the arithmetic here, and you should get 1.6 for the standard deviation there. Okay? So hopefully you see, rewind that, watch it again. Hopefully you see we used the first two columns to get the third one, multiplying them together. That, and then took the sum of it. That gave us the population mean here. We found x squared and then multiplied it times the second column to get the third column. The sum of the third column gave us this number here. And then we did the arithmetic and then took the square root of it and got 1.6, which is our standard deviation. Okay? Hopefully that makes sense to you. If you have any questions, please don't hesitate to ask your instructor.